Part A asks us simply for the systematic name of P4010. When it asks for a systematic name, if it's an organic compound, that just means the normal naming that you've learnt to do. But when it's an inorganic compound and it uses that word systematic, what it implies is that it wants you to specify using oxidation states. The point is that phosphorus oxide can be P4010, but it can also be P2O3. So those are both phosphorus oxides which are occurrent. There may be other ones as well. And to distinguish them, you recognise that the oxygen is always -2, but it's the phosphorus that changes its oxidation state, and you use that to specify which one it is. So you work out the oxidation state of the phosphorus. So we've got 10 lots of -2 there, which takes you to -20, and therefore the phosphoruses must add up to +20, and there are 4 of them, so it's 4 lots of +5. Okay, so we've got +20 -20 adds up to 0, as it must, because it's a neutral compound. So that's the oxidation state of the phosphorus, and that gets translated into a Roman numeral. So it's called phosphorus 5 oxide. Okay, and that's the systematic name. And then it wanted an equation for the reaction of that compound with PCl5 to make phosphoroyl chloride. So we've got those reacting together to make POCl3. So we could start with the chlorines. It's quite a good number, because you can see that's where it's going to be awkward, because you've got 3 on this side, 5 on that side. So the lowest common multiple is 15. So let's say, right, let's have 3 of those to give us 15 chlorines, and that means that we then have to have 5 of that. If we then look at the oxygens, you can see that we've got 5 on this side, and there seem to be 10 on that side. So you think, well, okay, how can we make that work? Well, of course the answer is, well, we can just have half there. And that balances, because you've got 5 oxygens on each side then. And then if we add up the phosphorus, we've got 3 of those, and half of 4 is 2, so 5 phosphorus on the left to balance the 5 on the right. So that's fine. Equally, you could double everything and have 6 of those and 1 of those to give you 10 of those, and that gets rid of the half, so that would be fine as well. Part C, it just asks us what's the atom economy of this reaction. And that's very simple in this case, because remember, atom economy is equal to the MR of the desired product divided by the sum of the MR of all of the products times 100. Well, there is only one product, so the sum of all one product is just itself, and therefore the atom economy is 100%. Okay, you don't need to get your calculator out for that one. If there's only one product, the atom economy is 100%. Okay, the next thing it asks for is a dot and cross diagram for POCl3. It's really got to be the phosphorus that goes in the middle there, because if you try putting oxygen in the middle there, oxygen can only make 2 normal covalent bonds, because it's in group 6, so it can only bring in 2 extra electrons. So the only way it could bond to 4 things would be by then donating its lone pairs to form dative covalent bonds. But it's really pretty rubbish at that, because it's a very electronegative element. It will cling on to its own lone pairs very tightly. So that really wouldn't work. Phosphorus, on the other hand, much less electronegative, and also, because it's in period 3, it can go beyond 8 in its outer shell, and that's really the crucial thing, which makes it the best candidate to put in the middle. So that means that we have an oxygen and 3 chlorines around it. So if we start with the 3 chlorines, they're straightforward. Chlorine needs 1 electron to reach its 8 in the outer shell, so that suggests that we just get 3 normal covalent bonds like that, with a dot and a cross each, and that would leave each of the chlorines with 3 lone pairs. Don't forget to put the lone pairs on. It's very annoying to do all the effort, make all the effort of figuring out the bonding and then lose the mark because you just missed the lone pairs off. So that just leaves the oxygen. Oxygen needs 2 electrons coming in to reach its 8, so that can be a double bond, which means that we have 2 shared pairs like that, and that will leave the oxygen with 2 lone pairs as well, so we get that. And we just have to check that's fine for the phosphorus. So it's used 5 electrons from the phosphorus, which is what it had, so that's fine. It has 10 in the outer shell, but that's okay, because it's only if you're in period 2 that you're restricted to 8. If you're below that, you can go up to 10. So that is the structure. You could, as an alternative, just put, let's get this right, this there. Okay, just put a dative covalent bond there in which the phosphorus is donating a pair of electrons to the oxygen, and that would leave an oxygen then with an extra lone pair like that. And that also works because the phosphorus now has 8 in its outer shell, and I think they would have to accept that as well. So either of those would do. The next question asks about the shape, and you're going to get the same shape in either case, because remember that a single bond or a double bond behave the same from the shape point of view. So it doesn't matter which of those you got, you're going to get the same shape. So let's have a look at that. Remember, the shape is dictated by electron pair repulsion, and that idea needs to be very clear in your explanation. So you focus on the middle atom and you say phosphorus has, and you list what it has in its outer shell. So in this case, it has 4 bonded pairs and no lone pairs. If we had used the other dot and cross diagram with the double bond there, we'd have said 1 double bond and 3 other bonded pairs plus no lone pairs. But the point is then, whichever of those you get 4 regions of electron density. And the key thing you must do is spell out that electron pairs repel each other. So you can just say it has 4 bonded pairs, no lone pairs, therefore 4 regions of electron density repelling each other. Because that's the key to the shape. It's not atoms repelling each other. If you say that, you're not going to get the mark. So what's the shape if you have 4 regions of electron density? Well, the answer is that you get a tetrahedral molecule. And a tetrahedron is drawn like this. So you put the phosphorus in the middle, you have 1 bond going up, 1 bond going across there, and 2 bonds going like that. So all 3 of these are angled somewhat downwards relative to that to make the point that this angle is bigger than 90 degrees. So that's the shape of your tetrahedron. It doesn't matter which atom you put where, so let's put the oxygen at the top and the 3 chlorines there. And using this version, this is a dative covalent bond, so we can draw it like that, or you could just have the double bond there. The same shape would be the same. And it also asked for the angle, and that you have to learn. You can't easily figure it out. I mean, you can figure it out, but not in the time you have in an exam. So 109.5 degrees is the tetrahedral angle. And that's everything you need for that question. Part F wants first of all to know whether we think POCl3 will be a good conductor of electricity at room temperature. It tells us it's a liquid at room temperature. So you know about 2 ways in which substances can be conductors. They can have delocalized electrons, which, because they're delocalized, are free to move, and that applies to metals and it applies to graphite. so it doesn't apply to that, so it hasn't got delocalized electrons. And you know that ionic substances can conduct, but only when they're in a liquid state, either molten or in solution. But this is not ionic, it's a simple molecular liquid. We've just drawn the dot and cross diagram to emphasize that it's made of individual molecules. So the answer is it's going to be a poor conductor of electricity, and you have to spell out that you know that because it will have no delocalized electrons and it will have no mobile ions, and therefore it has no means of conduction. Part 2 then wants us to calculate how many molecules of POCl3 there will be in this sample. So we've got 80.0 cm cubed at 120 degrees C, so that's above the boiling point, so it's now in the gas phase, okay, because it told us that the boiling point was 106, so at 120 it's going to be in the gas phase. And it told us that the pressure is 101 kilopascals. So obviously, if you want to calculate the number of individual molecules, first you have to calculate how many moles you have, and then you can turn that into the number of molecules. So the key to that, as soon as you see that you're given temperature and pressure, you use the ideal gas equation. You can't use 24 here because this is not room temperature. So PV equals nRT is the ideal gas equation, and what we have to do now is to rearrange that to find n. Right, so that's done easily because we've got to move these two terms over to the other side, and remember they just slide diagonally across. So we get PV divided by RT is equal to n. So then we just need the numbers to plug in and calculate that. So P is the pressure in pascals. So we have 101,000 pascals, okay, because it's 101 kilopascals, which is 101,000 pascals, times the volume has got to be in meters cubed. So we're given it in centimeters cubed, and you just need to know that to go from cm cubed to dm cubed, you divide by 1,000, which is times 10 to the minus 3. And to go from dm cubed to meters cubed, you do the same thing again. So again it's times 10 to the minus 3. And therefore the overall change to go from cm cubed to meters cubed is times 10 to the minus 6. Okay, it's important that you know those conversions. This is the only time we use cubic meters in chemistry, but it does come up a lot, so it's an important one to be able to do. So if it's 80.0 cm cubed, it'll be 80.0 times 10 to the minus 6 cubic meters. So that's your top line. R comes from your data sheet, is 8.314. And T is the temperature, but it's got to be in Kelvin. So 120 degrees C, remember you add 273 to get Kelvin, is 393 Kelvin. So we put 393 on the bottom line there. So it's important you write all those numbers out, and then crunch them on your calculator, and you should get 0.002473 moles. And that number needs to be there in case you mess up the next bit, because there's clearly going to be an intermediate mark for that one. And then you've got to turn that into the number of molecules. So then we use Avogadro's number. So you get that the number of molecules is equal to the number of moles times Avogadro's number. So that's 0.002473 times 6.02 times 10 to the 23. That number again comes from your data sheet, which comes to 1.49 times 10 to the power 21. It asks us for an appropriate number of significant figures here. So if you look at all the data that you fed in, 80.0. The reason it said 80.0 instead of just 80 is to make the point that that's 3 significant figures. If it had just said 80, it would have been 2 significant figures. So that's 3 significant figures. So is that. So is the pressure. And R, which you actually knew to 4 significant figures. So the limit, the lowest number of significant figures on any of the data you feed in is 3. And therefore the answer is given to 3, which is why I rounded it to that level. So that's your answer.